DSL. So the one way to increase the speed is to to make this line digital, the access line digital. And basically that's what the phone company did. You take the bits, actually you take the phone waves, and you take the computer bits and combine them and then send over and put a device here that can separate out the two. Basically these bits are coded at much higher frequencies. So this one is coded up to 4 kilohertz and this one is coded from higher frequency like 20 kilohertz to maybe 1 megahertz. So there is a frequency division multiplexing here, and then here those frequencies are taken out and then you can get the bits out. So basically this is what is called DSL. DSL stands for digital subscriber line, and this is your subscriber line. This is the line which goes from the phone company to the subscriber, which is your home. Once that becomes digital, that is called DSL, and now you are not limited to 56 kilobits. You can go up to as much as you want. I mean, I have a service at 18 megabits, which is the highest available in St. Louis. But as I said, in Japan and Korea and other places, you can get up to 100 megabits. Okay. And then this cable company can give you high speed too. Basically, what they do is they already have a cable which runs all through the streets and to your home, which is very high frequency, which is very high, which can pass very high frequencies. So they can use some frequency band for data, some for voice, and some for TV. For phone, all you need is 4 kilohertz. For video, you need up to 500 megahertz. And you need 6 megahertz for TV per channel. So if you have one channel, you need 6 megahertz. If you are getting a 70 channel from the cable company, you have to multiply that by 70. So 70 times 6, so that many megahertz. But the video cable is good. It can take up to 500 megahertz. All right, and therefore, given that we use one channel for data, suppose we use one channel for data and we do 5 bits per hertz. If we do 5 bits per hertz, out of 6 megahertz we can get 30 megabits. Normally the phone company, the cable companies offer service like this where 30 megabits down and 1 megabit up. The up speed is always lower for many reasons that we learn about when we learn about physical layer. So anyway, the down speed is 30, the up speed is 1. However, this cable does not go from your home to the cable company. What they do is they take it to some neighborhood and then they switch on to fiber, and the fiber goes to the cable company. So that is why it is called hybrid fiber coax, HFC. It's a combination of fiber and the coax cable. In some places they have moved forward and they bring fiber to the home, and that is called FTTH. In the case of fiber to the home, what happens is that the whole thing comes on a fiber, and then at some places they have what we call splitters. So the light that is coming from here goes to all the fibers that are split and goes to all the homes. So this is called optical line terminal, and this is called optical network unit, ONU and OLT. So everything that you want to send, that you want to receive, such as Ethernet or T1E1 or frame relay or telephone or video, all of that can be sent on the fiber. And since this is passive, goes to every home. Same thing goes to every home, and your ONU can select whatever is for your home and give it to you. All right, and since this is passive, passive means there is no electrical power required. This is a simple splitter. There is no electrical power required. This is very reliable. They can put it on the curves. If they needed a power there, then it can go bad and they have to send trucks to repair it and all that. So that's why this is also called passive optical network, PON, because of its reliability. So, like I said, I don't think we have in St. Louis FTTH, fiber to the home, but in some cities we do. And again, in other countries it's much more common. And again, the two countries that I keep telling you so many times is Japan and Korea. The next way to get to the network is wireless. And by wireless we have Wi-Fi hotspot, cellular access, telephone, or WiMAX. So WiMAX actually is a new network that is just coming up and actually available in St. Louis. And when you buy a computer nowadays, it might even have a WiMAX. My computer, for example, the one that is in front of me here, has a WiMAX chip in it. And Clearwire is offering the service here. If I were to get that service, it's like cellular service. I can go anywhere on the road, on the car, in the park, forest park, and I would be able to get very high speed access. Sometimes they call it 4G, which is a misnomer because WiMAX is 3G, but they call it 4G because it is much faster than 3G, the current 3G. So I mean, this is a names issue, but anyway. But the good thing about WiMAX is it goes as far as a cellular signal goes, but it goes at the speed at which Wi-Fi goes. The cellular signal is in terms of data rate, is very low rate data rate, right? But WiMAX gives you very high data rate like Wi-Fi. So it takes the best of Wi-Fi and the best of cellular. It takes the distance from the cellular, it takes the speed from Wi-Fi. So you can use it, you can basically, from one tower, you can light up almost a city, 4 or 5 kilometers. And you can even use it while moving, just like a cellular phone. That's all about the access. So we talked about the access, many different methods. We started with the modem, then we went to DSL, then we went to cable, fiber, and then the wireless. Those are all methods for access. So now we are back to networks, and then we want to measure the performance. So then we move on to this basically 3 methods of measuring the performance. Delay. First thing we measure about a packet is how long will it take, and so the delay consists of several parts. First is how long will it take. Say here's an example. So we want to send 640,000 bits over a circuit switch networks, and all the links are 1.536 megabits per second. Each link is shared by 24 users and 500 milliseconds to establish end-to-end circuit. So, since this is a circuit switch network, just like a phone network, before you can send your first bit, you have to set up the circuit. That takes 500 milliseconds. Once you have set up the circuit, then you can send either at 1/24th of this rate, in which case you just using 1/24th, you're a single user, or if you're a company, you could get the whole line for yourself, for the company, and you can send at that rate. This basically, the way phone line works is that the phone company right now takes 24 phone lines and puts them on one circuit. That is called a T1 circuit. Okay? Each phone line is 64 kilobits. What happens is whatever you speak is digitized at 8 kilohertz, 8,000 samples per second. Each sample is 8-bit long. So if you do 8 bits 8,000 times in a second, you get 64,000 bits per second. Okay? Now you take 24 users, so you multiply 64 by 24, you get 1536. Okay? That is one circuit that the telephone company uses, that is called a T1 circuit. If you are a company, you could just ask for a T1 circuit, you get 24 lines, and then you can use them for anything you want, for data, for voice, or whatever. Alright? So, if you look on the wire, what you will see is 24 slots. First slot for the first user, second slot for the second user, third slot for the third user, fourth slot for the fourth user. 24 slots in a particular time, and then cycle resumes again. Basically, then again 24 users. So all this happens, at a certain rate. And for example, in this example, we are talking about one user. So one user will get only 64 kilobit, and therefore to transmit 640 kilobit, it will take 10 seconds. If it was that it was a WASU, and WASU probably has many T1 links, right? We cannot live with just 24 phone lines. We need probably 200 telephone lines or something like that. So we have many T1 circuit, and so whatever rate you have, you just do that. Okay. And second thing is that these rates somehow will come into your brain. Like for example, for us who work on these things, we remember 1.536 T1, T3 is 45 megabits, T4 is something. All those numbers we remember because we work on them so often, right? But it will be clear whenever the problem is given to you as to what you have for usage.
It was just a contiguous sentence.
A sentence, okay, all right. Okay, all right, so now it will take 10 seconds to send that many bits, but it will take 0.5 seconds to set up the connection, so the total time for that file would be 10.5 seconds. On a circuit switch networks, you need to set up a circuit and then send the bits. On a packet switch networks, you don't need to set up the circuit. You can start sending the bits, but you have to packetize it, so there is an overhead per packet. So let's talk about packet switching. On the packet switching, first you have to collect the bits as they're coming in, make a packet, add the header, put them in the queue. So there is a queuing delay as well. So there is a queuing delay because you are waiting. First there is a processing delay, then there is a queuing delay, then there is a transmission delay, and there is a propagation delay. So what is transmission, what is propagation? Transmission is for the bits to get on the wire. You see, when you have packet which is so big, first bit gets on the wire, then the second bit gets on the wire, and the third bit gets on the wire. So let's say your packet is 512 bits, all 512 bits got on the wire, and then they move slowly to the destination. Right? So that is the propagation delay. Propagation delay is the delay to go on the wire and to move on the wire, right? And the transmission delay is the delay to get on the wire. Understand the difference? First, the bits have to leave the computer and get on the wire. That is transmission. Once they are on the wire, depending upon the length of the wire, they have to propagate. If the wire is 2,000 kilometers, there will be a lot of propagation delay. But the transmission delay will still be the same. Transmission delay simply depends upon how many bits per second you are transmitting and how many bits you have. Right? The propagation delay depends upon the distance. So that depends upon the distance and the speed of the signal. And the speed of the signal is speed of the light, which is 3 times 10 raised to 8 meters per second. That is also the speed of electricity. Well, actually, the speed of the signal changes on different things. So the speed of the light in vacuum is 3 times 10 raised to 8 meters per second, but if you are sending it on the fiber, it is only 2 times 10 raised to 8 meters per second. So you could have lines which are very long, you could have lines which are very short. You just have to know that there are 2 distances. One is the distance get on the wire, and second is so second is for the bits to reach the destination. There's no problem. Okay. So all right. So we have to consider 4 delays. Processing delay, which is basically inside the computer, where you have to check out everything, make the packets, and check the CRC. I mean, check that there is no error, nothing like that. Then you have to put them behind other packets. There might be a queuing delay. Then there is a transmission delay, and then there is a propagation delay. Okay. So as shown here, first there is something that you need inside the computer. Then you have to stand in the queue. Once you get your turn, then you have to get onto the wire, and then once you get on the wire, you propagate. So here is an example. You want to send 1500 bytes on 10 megabit per second Ethernet, and the length is 1 kilometer. So, first of all, transmission depends upon the packet size, because you want to get onto the wire. What is the speed? What speed we can get on? 10 megabits. And how long is the packet? 1500 byte. So how long will it take for the 1500 byte to get out of the computer at 10 megabit? It will take 1500 times 8. Why 8? Bits per byte. And divided by 10 mega. 10 times 10 raised to 6. That gives you 1200 microsecond or 1.2 millisecond. This is just the time that a packet takes to get out of the computer, get on the wire. Then the bits will travel to the other end, which is 1 kilometer away. And how long will it take for 1 kilometer? Since they are going on the fiber, we use the speed of 2 times 10 raised to 8. And this is 1000 meters, it takes 5 microseconds. Right? So it will take 1.2 millisecond for the transmission delay and 5 microsecond for the propagation delay. So that is the total delay. Actually, one delay which we have not calculated here is the queuing delay. It turns out, as you can see here in this example, the propagation delay is generally small. What is large is the queuing delay, which is not shown here. Queuing delay could be very large. You could be waiting inside the queue, particularly in a router where lots of people are sending the packets, and then they stand in the queue to get out of the router. Alright, so that finishes delay part. So the key lesson is that if it is circuit switched, you have 2 delays. What are those 2 delays? Circuit setup and then the transmission, right? Basically the propagation or whatever you want to call it, propagation delay, yeah. If it is packet switched, then there are 4 delays. First is the preparation time, second is the queuing delay, third is the transmission, and fourth is the propagation. Okay? Propagation depends upon the distance and the speed of the light. It does not depend upon whether you are going at 10 megabits or 100 megabits. You are still going 2 times 10 raised to 8. By the way, that number 2 times 10 raised to 8, we all remember how. That number, speed of light, there are 2 ways to remember it. One is that we remember that it is 3 times 10 raised to 8. That's kind of difficult to remember, but if you just remember 300 meters per microsecond, 300 meters per microsecond, that's much easier to remember. Because then the power goes away. 300 meters per microsecond. Second way we remember is actually, this is fiber thing which we use more often, is just this number. In our daily calculations, we know that it takes 5 microsecond per kilometer, period, that's it. 5 microsecond per kilometer. So if somebody says, well, I have a link which is 20 kilometers, we just multiply by 5 microseconds, and we know it is 100 microseconds. So those are the 2 numbers you can remember. Either 5 microsecond per kilometer for the fiber, speed of light in fiber, or if you want to know the speed of light, then 300 meters per microsecond. Either one. Alright, so now we move on to the next measure of performance, and that is throughput. Throughput is measured in bits per second. And somebody says capacity. Capacity means nominal throughput, and when we don't say capacity, we mean throughput, we means realistic. So what's the difference? The difference is nominal is what we use in the sales literature. That is the maximum possible. Actually, it is not even possible, but that is the rate at which we generally sell. For example, when you buy a Wi-Fi device, they say, let's say it is 802.11g device. They say it runs at 56 megabits. If you put it on your computer and measure, you will never get any more than 20 megabits. 56 megabit it is sold at, but you will never get any more than 20 megabits. So that 50 megabits per second is actually what is called nominal capacity. That is what each bit, if you were to take one bit in the air and measure it, it will be 56 megabit going per second. But you are not going to use every bit time there, because a lot of bit time on the wireless, you have to wait, you have to collide, and you have to retransmit, and so on and so forth. So what you really get in real, and there is a lot of bits which are lost in the headers. So what you really get as useful throughput is 20. So your throughput is 20 megabits, but the capacity is 56. So that is the nominal capacity, nominal throughput. Now, if you have many links along the path, your throughput will be determined by the bottleneck. So let's say you have 100 megabits to the first router, then there is a gigabit between two routers, and then 10 megabit to the next computer. What is the speed you will get on this path? 10 megabit. Right? So the end-to-end capacity is only 10 megabit. Actual throughput will be less due to sharing and overhead. But if suppose you have this connection, if you measure, you will not get 10 megabits even, because again some bits will be lost in the retransmissions and overhead and the packets and headers and so on and so forth. So that's the thing, yeah.
So, but it's still better, even though the worst, weakest link is 10 megabits. It's still better than if all three of those wires were 10 megabits, right? Because part of the journey is still faster.
Well, no. Okay, let me just say one more time. The propagation delay does not depend upon the speed. All right, propagation delay depends upon the distance, right? This 100 megabit does get the packets on the wire faster from here. This gigabit does get the packets from this router on the wire faster here. However, if you don't do things right, it is quite possible that a lot of packets can come in here at gigabits and they are not able to get out, so the queues are very big and the packets start getting lost. Okay? This was the problem 30 years ago when I did my PhD thesis, and that was one of the things that we worked on, congestion control. What should we do if this happens? And so nowadays it doesn't matter, because nowadays we have congestion control in the protocols. So if that happens, now we have protocols that will stop the source from sending any more rather than dropping the packets. But originally all we did was just drop the packet, and that was bad. Okay, so your observation is correct that if you given that you see, another reason you might need a gigabit line here is because not everybody is going here. Some of them might be going there, some other way, and so this line is in the center, and therefore it has to be high speed, and it is shared by a lot more people. But so that is correct, that it is better to have as high speed as you can get, although you have to be careful that if you have very unbalanced network, then you can get into trouble.
So what is it telling you that when you say that end-to-end capacity is 10 megabits?
Yeah, that means between this computer and this computer, between these two computers, you cannot send any more than 10. Between these two computers, but you can send another 10 to that other computer, another 10 to that computer, some other computer. All right. So, for example, when you have a DSL at home, you might have some speed. Let's say I have 18 megabits. So then 18 megabit is the maximum I can get from Google. Google has gigabit capacity, but I can't get that because I have 18 megabits. Period. Okay, so that's the end-to-end depends on the bottleneck. Now, So the third measure is the loss. If the packets get queued and they don't get out, then you have a loss. And so that, and also if the packets have bit errors, then there is a loss. If one bit in the packet goes wrong, then there are two possibilities: that you have an error correcting code and you can correct that bit, which most of us don't, by the way. And the networks, we don't use error correction. So only thing is the packet has to be thrown away. If we find a packet, every packet is checked, and if there is any single bit error, we just throw it away. Yeah.
What causes a bit error?
What causes a bit error is that, if you remember this coding thing, if I send this pulses and something like this, right, it is quite possible that depending upon the distance, this will become smaller and smaller and smaller pulse. At some point, the pulse will become so small that the receiver cannot recognize it. Okay, and that will cause a bit error. When you send it on the air, wireless, if somebody else sends it at the same time, that will cause a bit error. Right? Any interference will cause a bit error. Yeah.
How can you tell?
How could you tell? So we will talk about that when we go to the CRC, cyclic redundancy checks. So we put check bits at the end in every packet. If these check bits don't match, then we know that the bits are in error. It's like your credit card number. Credit card number, if you gave somebody credit card number, they don't have to go to the bank to figure out that this number, one digit was wrong, because there is a check digit at the end, extra digit.
Does the bias signal get weaker while they're waiting?
Okay, so the question is, does the signal get weaker while they're waiting? No. See, what happens when you're waiting, you're in the memory. In the memory, it is continuously being refreshed. But on the wire, there is no electricity. I mean, basically on the wire, it just, as it goes farther, it becomes smaller and smaller and smaller. But in the memory, it doesn't.